This is your presenter Asloob Mudassar, and I am presenting slide number 135 of the course on laser physics. Question is, in a broadband mode locked laser cavity, different components of cavity contribute towards positive dispersion and negative dispersion. Compensating techniques are implemented to nullify the dispersion. To understand dispersion-related issues and dispersion compensating techniques, first address phase and group velocities, group delay dispersion, limitation on pulse duration due to group delay dispersion, and then finally discuss at least one dispersion compensating technique. The answer is, this is the electric field that we have shown. E as a function of time and Z is equal to A naught e to the power iota omega t minus Bz. This is the phase factor omega t minus Bz. And you know that this phase factor remains constant. So we can set omega t minus Bz is equal to constant. So when omega t minus Bz is equal to constant, so as the time will pass, this term, that is omega t, will increase. So Z should also increase, so that due to this negative sign, omega t minus Bz remains constant. So it means that Z should be increased in the positive direction. So it means that this is a wave which is moving along the positive x-axis. So this E as a function of time and coordinate Z is equal to A naught e to the power iota times omega t minus Bz is a traveling monochromatic linearly polarized plane wave propagating in the Z direction with amplitude A naught. You see that it consists only a single frequency omega, so it is monochromatic. It has an amplitude A naught. I have shown this amplitude in the scalar form, but if you show this amplitude in the vectorial form, then of course this is a linearly polarized wave. And of course I have explained that this is moving along the positive Z direction because omega t minus Bz has to be constant, and it has an amplitude A naught with a frequency omega and propagation constant beta. In some notations you can see that you can see instead of beta you can see the wave number k over here, but both have the same things. Instead we are using a different notation beta over here. So beta is the propagation constant or the wave number, you may say. So beta can be defined as that beta is a frequency dependent. Generally it is a wavelength dependent, and implicitly you can also say that beta is a frequency dependent. Since we here we are showing that beta is a frequency dependent parameter and is known as the dispersion relation of the medium, that is the relationship between beta and omega will be referred to as the dispersion relationship. The phase phi t, which is equal to omega t minus Bz, phase for the traveling wave is omega t stands for traveling phase of the traveling wave is equal to omega t minus Bz of the traveling wave remains constant during the propagation. That is, when no dispersion is present, the phase has to be constant. So we can write that phi of t is equal to omega t minus Bz should be equal to constant. This the derivative of this one is d phi t is equal to omega times dt minus b times dz is equal to 0. So this gives, if you solve this equation and rearrange the term in the form of dz over dt, which we will label as phase frequency, phase velocity, v for the velocity, v ph for the phase. This is the phase velocity given by dz over dt is equal to omega over beta. So omega and beta will determine the phase velocity of the wave. This is the phase velocity or the velocity with which the phase wave front or the wave front, phase front or the wave front moves in space. So this is the speed of the phase front, or in general we can say the speed of the wave front in space, which is the phase velocity. So here we have defined the phase velocity. Now let's write an expression for the electric field of a traveling symmetric light pulse. You see that before that we have written the electric field of a traveling wave as given in equation number 1. This is the electric field corresponding to a traveling wave. But now we want to write down the electric field corresponding to a pulse of light. Now let's write an expression for the electric field of a traveling symmetric light pulse. The light pulse is symmetric and it is traveling, and we want to write down the electric field for that one centered at the frequency omega L. The light pulse contains, of course, not only a single frequency but maybe couple of frequencies, and omega L is the central frequency of the light pulse and having the bandwidth delta omega L. So delta omega L is the bandwidth, which means that it can contains many other frequencies besides the central frequency, which is the omega L. For the simplest case, we assume the following dispersion relationship. So for the pulse, which is symmetric and is traveling centered at frequency omega L, which has the central frequency omega L, and the pulse is traveling, we can write the phase dispersion relationship. We can write the dispersion relationship for such a pulse as beta minus beta L is equal to the derivative of beta with respect to omega evaluated at omega is equal to omega L multiplied by the factor omega minus omega L. Here omega is any other frequency present, any other frequency related to the pulse, and omega L is the central frequency of the pulse. Here we are assuming that the dispersion is present, that is the central frequency and any other frequency on the pulse can move with the different phase velocities. So here this is what we have written down the relationship between them, where beta L is the value corresponding to the omega L. So let me show you the proof of this one. That is the derivative. That is the derivation of this equation. That is the derivation of equation number 3 in appendix. So this is the appendix and we are going to show the derivation. So you see that we are considering that phi t is written as omega t minus bz is equal to constant, and omega is any frequency on the pulse. And here we have also written the same relationship for only the central frequency, that is omega L. Omega L into time, omega L times t minus BL times Z is equal to constant. And BL is the parameter related to omega L. So here we are considering that both are constant because we are assuming that no dispersion is present in the system. We can take the derivative of this quantity, that is t with respect to omega. So we have t minus derivative of beta, that is d beta over d omega times z is equal to 0. And we can solve it for t, which is t is equal to derivative of beta with respect to omega times z. And we can more explicitly write in the form that t is equal to derivative of beta with respect to omega evaluated at omega is equal to omega L times z. So this will hold generally for any value of omega on the pulse, and for any particular value of the omega, that is with the central frequency. This also holds for the central frequency, and in general holds for all the frequencies present in the pulse. So we can substitute the value of t in both of these expressions, that is in this one and also in this one. That is, we can replace time with this factor. So we can write the two terms as, so we have phi t. From the first expression we have this relationship, and eliminating the time in the second expression, for example over here you have this expression. Now you can subtract the two waves and you will get this expression, that is W minus WL, omega minus omega L times d beta over dW times Z minus beta L times Z. So you can see that Z is present in both the terms. We can eliminate Z from here, and the rest of the equation becomes equal to this one. We can solve this equation for the value of beta minus beta L, eliminating Z also, and we have beta minus beta L is equal to d beta over d omega evaluated at omega is equal to omega L times omega minus omega L. So you see that this is the dispersion relation that we have written, and we have developed the relationship between the two values of the beta. So this beta corresponds to any value of omega on the pulse, and this value of beta L corresponds to the central frequency of the pulse. Okay, so this is the dispersion relation that we have proved over here. So let's go back to equation number 3. Okay, so for the simplest case, we assume the following dispersion relationship for the pulse. That is beta minus beta L is equal to the derivative of beta with respect to omega times omega minus omega L. So this is what I have given you a proof of this equation. Where beta is the value corresponding to omega L, the electric field of the pulse can now be written as. So you see that it is the time to write down the electric field, because we have written the dispersion relationship for the pulse. Now we can write the electric field of the pulse also. That is E as a function of time, and Z is equal to A, that is the amplitude, which is the function of T minus Z over Vg, where Vg is the group velocity, times e to the power iota times omega L times t minus beta L times Z. So you see that actually this is in principle the same relation that we have written for a traveling wave given by equation number 1, except that we have written a naught, that is the amplitude, explicitly in a different form, and we have replaced omega by omega L and beta by beta L in order to represent the central frequency of the pulse. So for the central frequency of the pulse, we can write this relationship. So if you write omega instead of omega L and beta instead of beta L, it means that this would be the electric field corresponding to any frequency omega on that pulse, where the pulse propagates at a speed Vg, where Vg is the group velocity without undergoing any shape change, and is given by. So Vg, the value of the Vg, that is the value of the group velocity, is equal to dw over d beta, time evaluated at beta is equal to beta L. Vg is called the group velocity. The pulse being a function of, now you see that we have written the pulse in this form, where the amplitude has been written that A is a function of T minus Z over Vg, and then this is the traveling phase factor e to the power iota omega L times T minus beta L times Z. So let me show you the derivation or the proof of equation number 4 using the appendix. So let me start with this equation, this one. So from this one, I am writing equation in appendix number 2. So I have written T is equal to the derivative of beta with respect to omega times Z. So you see that this is what I have taken from appendix 1. And this is the derivation, this is the definition of the group velocity, that is Vg is equal to d omega over d beta evaluated at beta is equal to beta L. This is the definition of the group velocity. Now you see that I can introduce this Vg in this expression by taking the by inverting this relationship. So I have T is equal to 1 over Vg times Z, because I have inverted it. I have inverted the expression this one, and I have introduced Vg in the form of 1 over Vg over here. So this is the relationship, and I can write T minus 1 over Vg times Z is equal to 0. So this is the factor T minus 1 over Vg, or I can write T minus Z over Vg is equal to 0. And you see that this is the term that I can introduce in the amplitude form. So the amplitude can be written as A naught is equal to A times T minus Z over Vg, because now the amplitude will be the function of these parameters. So this is what I have introduced in my lecture. So in the electric field of the pulse, I have introduced this factor. So Vg is the group velocity, and the pulse being a function of this, that is A times, that is not times, that is A as a function of T minus Z over Vg times e to the power iota, and within parentheses we have omega L times T minus beta L times Z. So this is a carrier wave, which indicates, or the carrier pulse you can say, which indicates that the pulse is propagating along the positive Z direction. because the previous expression for the electric field we have written for the pulse. The pulse will travel the medium of length L in a time tau g given by. So if you want to calculate the time tau g for which the pulse will travel a distance L in the medium, you can write that tau g is equal to L over Vg, where Vg is the group velocity. And substituting the value of Vg from this equation, where we have introduced Vg in equation number 5. So introducing the value of Vg, you can write this expression as tau g is equal to L over Vg is equal to L into derivative of beta with respect to omega. And you see that this can also be written as a phi prime at a value of omega L. So I have written is as a phi prime, that is the derivative of a phi with respect to omega. So this phi prime is actually the derivative of a phi with respect to omega. But you see that I have written over here two signs, is equal to 0 and is not equal to 0. So this quantity will be equal to 0 when the dispersion is not present. Then we need to set phi prime is equal to 0 because the phase will be constant under that condition. But if the dispersion is present, then you see that different parts of the pulse will move with the different velocities, and under that condition we can write that this quantity, that is the derivative of phi prime, that is the derivative of phi with respect to omega, written as phi prime, will not be equal to 0. So this is not equal to 0 is applicable in our case because we are including the dispersion in our process. So we can retain this factor. So combining the last two quantities, so we can write L. So this d beta over d omega can be written as L times d beta over d omega, and phi prime can be written as d phi over d omega. So you can omit the derivatives and you can write this quantity as a phi is equal to beta times L. And you can generalize this one, that phi as a function of omega minus omega L is equal to beta as a function of omega minus omega L times L. So either you can take at read as phi is a function of omega minus omega L, or if you even assume that this factor has been multiplied on both sides, that is phi multiplied by omega minus omega L is equal to beta multiplied by omega minus omega L, then times L, this would also be correct. So phi as a function of omega minus omega L, or phi multiplied by omega minus omega L, under both these conditions equation 7 can hold. So Vg is usually smaller than C, which makes tau g relatively longer. So you see that here Vg, which is the group velocity, is usually smaller than the velocity of light, and then under that condition tau g is relatively longer. So tau g is a measure of the time delay of the pulse. So we are using this tau g repeatedly. So remember that tau g is actually a measure of the time delay of the pulse, known as the group delay of the medium at omega L. So far we talked about one pulse. We wrote down the phase relationship between the pulse, and we also discussed different other parameters. Now we are going to discuss the case of two pulses. Now let us consider two pulses in the same medium with central frequency omega or central frequencies omega 1 and omega 2. That is, for the pulse 1 the central frequency is omega 1, and for the second pulse the central frequency is omega 2. And assuming that omega 2 is greater than omega 1 with the corresponding bandwidths, delta omega 1 is the bandwidth of pulse 1 and delta omega 2 is the bandwidth of pulse 2. The pulses travel at two different group velocities, Vg1 and Vg2. If these two pulses enter a medium of length L and their peaks overlapped initially, they will be separated in time with a delay between them given by. So here you see that we are assuming that there will be a delay between the two pulses. Initially they will be overlapped, and when they have traveled through the medium, then of course they will be separated well apart from each other, or separated from each other, and the separation is given by delta tau g. Delta tau g is actually the time delayed separation between the two quantities. So delta tau g is equal to phi prime. You see that I have written tau g in the form of phi prime. Tau g is in the form of phi prime. So for one wave we have tau g1 and we have phi prime of omega 1. For the second pulse we can write tau g2 and we have phi prime of omega 2. So if the times are different due to the dispersion, then we can write time tau g1 minus tau g2 and we can write delta tau g in this form. So delta tau g is equal to phi prime for the pulse with the central frequency omega 2 minus phi prime for the pulse with the central frequency omega 1, because we are assuming that omega 2 will travel faster than omega 1. So we have I am multiplying this left hand side on both sides by the quantities, dividing and multiplying with omega 2 minus omega 1. So I have written this expression. Now you see that this term, that is phi prime omega of omega 2 minus phi prime at omega 1 divided by omega 2 minus omega 1 is actually the definition of the derivative. And using the definition of the derivative, I can write it as phi double prime. So this is the phi double prime evaluated at omega 1. And then the rest of the factor is this one, which is omega 2 minus omega 1 has been written as such. So you see that I have used the derivation of the definition of the derivative, and I have converted the single derivative into the double derivative, which is a phi double prime. So actually this phi double prime is equal to d phi over d omega d square phi over d omega square, evaluated at the central frequency omega 1 of the pulse 1. If this equation is valid, then phi and omega can be related as given by the following equation. So you see that we can also write down the phase relation, that is the dispersion relationship for these two pulses. That is phi minus phi L is equal to d phi over d omega evaluated at omega L. And then we have omega minus omega L plus a half of d square phi over d omega square evaluated at omega L multiplied by square of omega minus omega L. So you see that we have included the dispersion up to the second term. So this is the second order dispersion we have included. This is the first order dispersion that we are talking about. So you see that when the pulse will travel, and if we want to include the second order dispersion, we need to write down this relationship for such a pulse. So this is the equation number 9, and I am going to show you the derivation of this pulse in the appendix. So we have phi is equal to omega t minus bz, which is the phase for the traveling wave. And if you write down it for the frequency L, which is the, for example, the central frequency of the pulse, omega L is the central frequency of the pulse, and omega is any other frequency on the pulse. So if you write it for the central frequency, then you can write phi L is equal to omega L times t minus beta L times z, and beta L is a parameter corresponding to omega L. So you see that I have written phi for the same pulse, but at any for any frequency omega, and for the central frequency omega L. So these two factors have been written for the same pulse. So if you now represent the derivative of this quantity, then phi prime will be equal to phi minus phi L over omega minus omega L. So this is what I have used the definition. By definition, the derivative is defined by this quantity, where of course the separation between omega and omega L is small. Under that condition, this will give you the definition of the derivative. So the derivation, the same definition of the derivative obtained from this second expression is shown over here. So phi L prime is equal to phi L minus phi over omega L minus omega. And you know that by definition, the second derivative can be written as phi prime minus phi prime of L divided by omega minus omega L. So I have written this in the term in blue as a derivation, as a derivative of the first, as the definition of the derivative for this phase factor, and for this phase I have written the derivation, the definition of the derivative in red, and this is the derivation. This is the this is the definition of the double derivative in terms of the single derivatives. This is expression. Now you see that I am going to solve this one, this quantity, that is the double derivative, substituting the values of the single derivatives. So I have substituted the derivative of single derivatives obtained earlier, that is the derivative in the form of a blue term and the derivative in the form of the red terms. So you see that this is just a manipulation, that is I have written a plus sign in the center and I have multiplied by the negative sign within the in the denominator, so that I can write the two denominator to be in the same form, that is omega minus omega L and omega minus omega L, that, so that I have made the two denominators to be equal to each other by putting a positive sign and multiplying the negative sign inside the denominator. So you see that in the upper term, in the denominator, I am introducing the terms in the red. So I have phi L minus phi, and I can write this one as a phi minus phi L, and I am subtracting from this one 2 times of phi minus phi L. So you see that if you solve this numerator, you will get the same expression as phi L minus phi. So what I am going to do next is that I am combining, this is the first term is in the numerator is phi minus phi L. The second term I have created in the red is also phi minus phi L. So I am combining the first two terms in the numerator with and adding them, so it becomes 2 times of phi minus phi L divided by omega minus omega L, and the term which is left is minus 2 times of phi minus phi L divided again by omega minus omega L, and the two terms in the numerator is also divided by omega minus omega L. So you see that now I am writing down the next term. For example, you can see that over here that this is the same thing that I have written, but the difference is that I have written in the form, but of course I have multiplied this omega minus omega L to this, that is I am combining the two the denominators, and combining the two denominators I have this expression. So there over here, so actually this should be omega square over here. So I have forgotten to write down omega square over here. So this should be omega minus omega L square. But you see that here I have written correctly, that is phi double prime is equal to 2 times of phi minus phi L divided by the square of omega minus omega L, and minus 2 times of phi minus phi L divided by the omega minus omega L whole square. But over here you should also have omega minus omega L whole square, but I have corrected it in the next step. So this is the correct step. Now you see that I am going to make a substitution over here. Phi minus phi L from the blue expression above, I can write it as phi prime of omega minus omega L. For example, you can write from here phi minus phi L can be written as phi prime multiplied by omega minus omega L. So making this a substitution, that is replacing phi minus phi prime with the term 2 times of phi prime multiplied by omega minus omega L. So one of the omega minus omega term will be cancelled out in the denominator, and then you have these terms. So phi double prime is equal to 2 times of phi minus phi L divided by omega divided by the square of omega minus omega L, whereas in the second term we have a minus 2 phi prime over omega minus omega L, because this contains only one factor of omega minus omega L in the denominator. Now rationalizing them, that is multiplying the whole dividing the all the three terms on the all the three terms by 2, and multiplying all the three terms by the square of omega minus omega L, we get this expression. Now we can solve this expression for the value of phi minus phi L, that is solving this one, moving this factor on the other side, we have this expression. So phi minus phi L is equal to phi prime multiplied by omega minus omega L plus a half of phi double prime and the square of omega minus omega L. In terms of the derivative, you can write this expression as phi minus phi L is equal to d phi over d omega times omega minus omega L, and this can be written as half times d square phi over d omega square times omega minus omega square of omega minus omega L. So this is the equation number 9, and you see that this is the dispersion relation for the same pulse, and we have written the dispersion relation including up to the second order dispersion. So this is the first order dispersion, this is the second order dispersion for the single pulse. So let's go back to equation number 9. Okay, so you see that I have explained that how we wrote down the dispersion relation for the single pulse. Now consider a pulse with the different spectral regions. That is, the pulse consists of course, different frequencies traveling with the different group velocities. So here we are assuming that a pulse, of course, consists of different spectral regions, that is consists of different frequencies, omegas, and traveling with the, and now we are assuming in addition to that one, that is the waves, that is different pulses, that is different frequencies in the pulse are traveling with the different group velocities. That is when the dispersion relationship is a parabolic, the pulse broadening, you see that this dispersion relation that we have written in equation number 9 is of the parabolic form. So when the dispersion relation is a parabolic, the pulse broadening, which we can write as delta tau d, because when the pulse will travel different frequencies, when the pulse will travel with the different group velocities, the resulting pulse will of course be broadened, and here we are talking about the pulse broadening by the factor delta tau d due to the dispersion is found from the difference in group delay between fastest and the slowest spectral components. So here we are writing the pulse broadening delta tau d can be defined approximately to be the mod value of the double derivative at omega L multiplied by delta omega L. Because here we are considering only the fastest component of the pulse and the slowest component, the slowest spectral component of the pulse, and we are subtracting the two fastest and the slowest in order to write down the group delay between them, and then of course we can write down the pulse broadening delta tau d is approximately equal to the mod of phi double prime evaluated at the central frequency of the pulse multiplied by delta omega L, that is the difference of the frequencies with respect to the central frequency, where phi double prime evaluated at omega L is the group delay dispersion. So phi double prime is the group delay dispersion of the medium at omega L. Its magnitude is a representation of the pulse broadening per unit bandwidth of the pulse. So this double prime, phi double prime, will give you the pulse broadening per unit bandwidth of the pulse. The double derivative of phi can be computed from equation number 7, and equation number can be written 10 can be written as, so we can compute equation number double derivative using equation number 7. Let me show you equation number 7. So this is equation number 7. You can compute the double derivative of phi from equation number 7, and substituting that one into equation number 10, we can write the final expression for tau d as delta tau d is equal to is approximately equal to L, where L is the length which for which the pulses has traveled the distance due to which delta tau d was produced. So L is the distance that the pulse has traveled. So delta tau d is equal to L times the mod of second derivative of beta with respect to W, that is d square beta over dw square, and outside this mod we have delta omega L. So just we have replaced the double derivative in the previous equation by the derivative in the explicit form. Now this d square beta over d omega square evaluated at omega is equal to omega L is known as the group velocity dispersion at omega L. And using equation number 6, it can be expressed as, so let me show you equation number 6 first. This is equation number 6. So you see that in the equation number 6, we have the same parameter, that is d beta over d omega. And you see that Vg is also present over here. So it means that using this factor, we can represent the coming equation in the form of Vg, that is the group velocity. So we can write equation number 11 in the form of equation number 12 using equation number 6. So d square beta over d omega square can be expressed as the derivative of 1 over Vg, that is the derivative of 1 over g with 1 over Vg with respect to omega, as shown in equation number 12. So we can, if you want, you can use equation number 10 in equation number 12 in equation number 11. Its magnitude is a representative of the pulse broadening per unit length of the medium per unit bandwidth of the pulse. So you see that this is what we have discussed, single pulse. And when that single pulse travels a distance, length L, a distance L, then of course a delay will be produced, and we have shown that delay between the that is the broadening of the pulse has been shown in equation number 11. Next, we discuss the limitation on pulse duration due to group delay dispersion. Consider a mode locked laser cavity of a ring type consisting of a passive self-amplitude modulation element in the form of a fast saturable absorber. You know that I have discussed a fast saturable absorber in one of the previous slides. If you want to see the detail, you can consult my previous slides. Under steady state pulse propagation, steady state, what is the meaning of steady state pulse propagation? That is the pulse is not broadened when it travels. That is called steady state pulse propagation. The pulse broadening must be compensated by pulse shortening. You see that I have in one of my previous slides, while discussing the mode locking techniques, I have discussed pulse shortening and pulse broadening mechanisms. That the pulse shortening is done when the mode locking elements is in place, and the pulse broadening happens when it passes through the active medium. And here you see that besides the active medium, we are also including a dispersive medium. So here we have actually the three mediums that we are going to consider. One medium is going to compress or shortening the pulse, compressing the pulse, whereas the other two mediums are going to broaden the pulse. So let me explain them. The relative time shortening represented by delta tau p over tau p, where tau p is the time of the pulse peak, and this S stands for the shortening of the pulse. So when the pulse will pass in the net gain window, you see that when we place our active medium over active mode locking techniques, we have a window which called the net gain window. This net gain window has also been explained in one of my previous slides. So if you are in the net gain window, this has been defined as delta tau p over tau p with a subscript s. So this stands for in the net gain window, this will be equal to the shortening of the pulse, because the pulse is shortened when it passes through the net gain window. And for that one, you can consult slide number 134 and figure number 3 there. So this time shortening in the net gain window must be equal to the pulse broadening in the gain medium, which is the active medium rod, for example, in the gain medium, and broadening of the pulse in the gain medium is, for example, given by delta tau p over tau p evaluated at the gain medium, and G represent the gain medium, and the pulse broadening in the dispersive medium, that is the delta tau p over tau p, and D stands for the dispersive medium. So we have here the three mediums, that is the net gain window, we have the gain medium and we have the dispersive medium. The dispersive medium is the medium which could be in the present in the laser cavity or in the laser cavity. So gain medium and the dispersive medium are responsible for the pulse broadening, whereas when the pulse is generated in the net gain window, then this will compress the this will automatically the automatic mechanism of the passive mode locking will compress the pulse. So this pulse compression should be balanced by these two pulse broadening mechanism in order to ensure the steady state pulse propagation within the laser cavity. Let us assume that the pulse has Gaussian intensity profile with the full width half maximum width represented by delta tau p. This is that we have also discussed delta tau p. You know that I have also given you a relationship for the delta tau p over here. You see that in one of the slides I have given the relationship of delta tau p. Or maybe in the appendix, for example, I have discussed that one. Okay, so let us assume that the pulse has a Gaussian profile, intensity profile with full width half a maximum width delta tau p. The pulse will pass through the gain medium, dispersive medium, and passive mode locking element. The group delay dispersion of the dispersive medium at frequency omega is defined by phi double prime of omega. So this is the group delay dispersion due to the dispersive medium, and it is given by phi double prime of omega, and phi double prime of omega is what we have discussed earlier. The homogeneously broadened gain medium is described by its single pass saturated gain given by G naught is equal to N naught times sigma times L. Having a full width half maximum line width delta omega naught, and delta omega naught is defined as 2 pi times delta nu naught. So delta omega naught is the full width half maximum line width of due to the gain medium, due to the gain at the gain of the pulse, and this is in terms of the linear frequency delta nu naught. For small changes in delta tau p, we can obtain the following expressions. So delta tau p over tau p for the gain medium is equal to 2 log of 2 divided by pi square multiplied by the factor 1 over delta tau p square times delta nu naught square, and multiplied outside with the G naught, where G naught is the gain of the medium. And this is the relationship that we have written, that delta tau p over tau p for the dispersive medium, D for stand for the dispersive medium. So this expression for the dispersive medium is equal to 8 times log square of 2, and then outside that we have phi square of the double derivative of phi divided by the fourth power of delta tau p. For the steady state condition that I have also discussed, that delta tau p due to S, that is the shortening of the pulse, is equal to should be compensated by the broadening of the pulse, and the broadening elements are delta tau p over tau p at evaluated at G, that is evaluated at the gain of the medium, plus delta tau p over tau p evaluated at the dispersive medium. So the term on the right hand side, that is D, two terms are responsible for the broadening of the pulse, whereas the term on the left hand side is responsible for the shortening of the pulse. And if the equation number 15 is satisfied, then the shortening of the pulse is balanced by the broadening of the pulse, and then the steady state operation is carried out. That is, the pulse is neither broadened nor shortened when it travels under the steady state condition. So using equation number 13 and equation number 14 in the numerical form, the equation number 15 takes the following form. So the numerical form of equation number 15 becomes as given in equation number 16. So delta tau p over tau p at S is equal to 0.14 times G naught over delta tau p square, delta nu naught square plus 3.84 times square of double derivative of 5 divided by the fourth power of delta tau p. So you see that the first term, the one term I have shown in red, the other term is I have shown in blue, because I am going to have a discussion about these two terms. As delta tau p decreases, you see that delta tau p is present in the denominator of the both terms, one with the second power and the other with the fourth power. So as delta tau p decreases, the second term shown in blue on the right hand side becomes more important. So if delta tau p decreases, then effectively this term becomes more prominent. The pulse width at which second term on the right hand side, that is the group delay dispersion, starts becoming more significant can be obtained by equating the two right hand side terms, which gives. So you see that if you want to understand that under what condition that this term is going to be dominated, then you see that you can equate these two terms in order to find out the value of the delta p. So why we are equating these two terms? Because we want that this term, which is the second order group delay dispersion, that is the dispersion term, so should cancel out this term. That is the blue term should be negative term, and it should cancel the term in red, so that these two terms cancel out with each other. That is, we should need to produce negative dispersion. So when the negative dispersion is produced, this will cancel out the broadening mechanism due to red term, and then this term, that is the shortening of the pulse, becomes equal to 0. So for that one, under that condition, if you equate these two terms, you will get delta tau p is equal to 27.4 divided by g naught raised to power 1 by 2, and then the mod of phi double prime multiplied by delta nu naught, as shown in equation number 17. So this is delta tau p is the time. So the pulse width at which the second term on the right hand side, that is the group delay dispersion, starts becoming more significant can be obtained by equating the two right hand side terms, which gives you delta tau p equal to this one. So you see that this time delta tau p is the time which is very important, for which we have calculated, and we have calculated this one under the condition that the two terms will cancel out each other. To reduce delta tau p, we must reduce GDD contributed by phi double prime. So if you reduce the value of a phi double prime, of course you can reduce delta tau p. Equation number 17 shows the dependence of delta tau p on the second order group delay dispersion. So this derivative represents the second order group delay dispersion. If higher order dispersion terms are included, they must also be compensated. So you see that in the above equation, that is in equation number 16, we have included the group delay dispersion up to the second term. So if you include even the higher order terms, then you must develop a mechanism for the compensation of those terms also. That is, the right hand side should vanish out. Now we discuss dispersion compensation. So you see that how we can compensate the dispersion in practical sense. This is what we are going to discuss. In broadband mode locked lasers, different cavity components including active medium and mirrors, etc., contribute significantly towards the dispersion. So here we are talking about just only two components, that is the active medium rod and the mirrors. They contribute significantly towards dispersion. Such cavities require dispersion compensating elements to be inserted inside the cavity So if we want to nullify the dispersion, we need to insert some dispersion compensating elements. If quartz crystal is a component of a laser cavity, it would exhibit positive normal dispersion. You know that quartz crystal, if it is a part of a laser cavity, then this will contribute towards positive dispersion, which we normally take as normal dispersion. To compensate dispersion, an optical element with an equal but negative dispersion, which we call as anomalous dispersion, should be inserted inside such cavities. So now the question is that how we can design our component a negative dispersion, how we can introduce an element that would introduce negative dispersion within the laser cavity, so that we can cancel out all the other positive dispersions. In order to cancel out the negative dispersion, we are going to use an optical element. Let me, before describing page number 8, I am going to move towards page number 9 so that I can describe this optical system. So let me read the caption first. A combination of 4 identical prisms providing negative and controllable second order group delay dispersion. So you see that this optical system provides two things. That is, it will generate negative dispersion of second order, and second is that it will provide you a control over the second order group delay dispersion. That is, you can control the magnitude of the dispersion. You can see that there are 4 prisms labeled with the prism 1, prism 2, prism 3, and prism 4. And in between them, I have drawn a vertical line, dotted line marked as MM prime. So this line is actually perpendicular to the path of the light beam between prism 2 and prism 3. And it also separates out prism 1, the prism 1, prism 2 from the set of prism 3 and prism 4, because this provides that the path of the rays on either side of this dotted line is symmetric. So you see that here I have 2 pulses with central frequency omega 1, and the second pulse has a central frequency omega 2. These 2 pulses are entering into the prism with the assumption that they are coinciding with each other while entering into the prism 1, whereas omega 2 is greater than omega 1. So you see that the path of the prism is shown, that is, they are now separated into different paths due to the frequencies between them. And when these 2 rays will enter into the prism 2. The path due to omega 2 is represented by the upper path. The upper path represents the path of the pulse due to omega 2, whereas the lower one represents the path of the pulse due to omega 1, central frequency omega 1. So through the prism 2 they will travel, and then they will enter the prism 3, and from the prism 3 the light will travel towards the prism 4. And you can see that when they exit the prism 4, the 2 pulses are separated from each other. That is, you have produced a group delay between them, and they are separated. Initially, the 2 pulses were collinear with each other, and also they were matching with each other. That is, they were overlapped. Here, the pulses are also collinear, but they are separated from each other because omega 2 was greater than omega 1, and you can see the separation between them. And this dotted line, you can see, indicates that the light has traveled in the same path, that is, the path of the light has not changed. So this is the setup that you can insert in a laser cavity without any change of the path of the beam. But you can also produce a separation between the 2 pulses. So now I am going to describe the mechanism of this diagram. A combination of 4 identical prisms arranged in figure 1 provide a negative and controllable second order group delay dispersion. The prisms satisfy the following properties. All the prisms are oriented for minimum angle of deviation. So this is one property that the system should present or exhibit. The apex angle of each prism is such that the rays enter and leave the prisms at Brewster angle. Second condition. The entrance phase of the prism 2 is parallel to the exit phase of prism 1. The entrance phase of prism 2 is parallel to the exit phase of prism 1. You can see that this phase is parallel to this phase of the prism. And also you can notice that the exit phase of prism 3 is also parallel to the entrance phase of prism 1. The entrance phase of prism 2 is parallel to the exit phase of prism 1, and the exit phase of prism 2 is parallel to the entrance phase of prism 1. The same also holds, and the exit phase of prism 2 is parallel to the entrance phase of prism 1. That is, the exit phase of prism 2 is parallel to the entrance phase of prism 1. So the entrance phase of prism 1 and the exit phase of prism 2 are same, and the entrance phase of prism 2 and the exit phase of prism 1, they are also parallel to each other. The same is also true for the other set, that is for the set containing prism 3 and prism 4. The same also holds for the set of prisms 3 and 4. The midway bisector represented by MM prime line is a plane of symmetry for the ray paths. That is, the MM line represents the symmetry of the rays on either side. In the figure, the two pulses at omega 1 and omega 2 with omega 2 greater than omega 1 enter the prism 1 at the same time along the same direction and initially along the same path. The pulse omega 2 traverses a shorter path. Both pulses exit the prism 4 along the same path and in the same direction, with the pulse at omega 1 delayed in comparison with the pulse at omega 2. So this is the delay that I have also shown in the figure. That is omega 1, that is the pulse with the central frequency omega 1 is delayed in comparison with the pulse 2 having central frequency omega 2, where omega 2 is greater than omega 1. The exit path of two pulses from the prism 4 is collinear, that is, they have the same direction, with the path of the two pulses while entering the prism 1, and this is indicated by the dotted line. So you can see that the dotted line over here indicates that the direction of the propagation of the pulses has not been changed. We can write that tau g for the second pulse is shorter than the tau g for the first pulse. That is, tau g of omega 2 is less than tau g of omega 1, because omega 2 will take shorter time, and we can calculate delta tau g, that is the difference between the group delayed velocities, is equal to tau g at omega 2 minus tau g at omega 1. And you can also represent tau g in terms of the parameters that we have also discussed, that is in terms of phi prime of omega 2 minus phi prime of omega 1. And this can also be represented in terms of the phi double prime of omega 1 multiplied by the factor omega 2 minus omega 1. So I have used previous equations in order to write down this relationship. So this is the relationship by as obvious from the equation, that is delta tau g can be defined as tau g at omega 2 minus tau g at omega 1, and the next two relationships I have obtained by using the previous relationships that I have discussed in the presentation. It follows that delta tau g is negative, that is less than 0. Then the phi double prime is also has to be less than 0. That is, the group delay dispersion is negative. So you can see over here that delta tau g at for the second pulse, that is for at omega 2 is shorter than this one. So this quantity is smaller than the other quantity which is being subtracted. So delta tau g is a negative quantity, and which means that phi double prime is also negative, has to be a negative quantity. So it follows that delta tau g is less than 0, which means that phi double prime is less than 0. That is, the group delay dispersion is negative. It can be found that phi double prime depends linearly on the distance L between the prism 1 and 2 or between the prism 3 and 4. By changing L, the separation between tau g at W2 and tau g at W1 can be changed. That is, the magnitude of the negative group delay dispersion can be controlled coarsely. That is, in the coarse sense, you can control the GDD. That is, the negative group delay dispersion can be controlled by changing the separation between the prisms. So if you make the separation between prism 1 and prism 2 to be increased, or the separation between 3 and 4 to be increased, you can increase the separation and you can coarsely control the time of delay, time of propagation of the pulses 1 and 2. And in terms of that one, you can also you control the negative group delay dispersion. Now, this is what I have mentioned, how you can control the group delay dispersion on coarse basis. Now, a fine control over the negative group delay dispersion can also be achieved by moving any of the prisms in a direction perpendicular to its base as indicated by an arrow on the prism number 2. So let me show you. You can see that I have marked this arrow on the base of the prism 2. So if you move this prism in the direction of this arrow or opposite to the direction of this arrow, you can very precisely control the negative group delay dispersion can be very precisely controlled. Similarly, you can also put these arrows on the other prisms, and you can also move the other prisms perpendicularly to the direction of the bases of these prisms. So let me read again. A fine control over the negative group delay dispersion can also be achieved by moving any of the prisms in a direction perpendicular to its base as indicated by an arrow on the base of prism 2. As the beam incident on prism 1 and the beam exiting the prism 4 are collinear, the combination can be inserted in a well-aligned laser cavity without any disturbance. So it means that the setup that I have shown you can be placed in any of the laser cavity without disturbing the parameters of the laser cavity, and instead you can introduce negative group delay dispersion in the laser cavity. A half combination can also be used. That is a combination with prism 1 and prism 2 or prism 3 and prism 4 can also be used. A half combination consisting of a prism 1 and 2 can also be inserted in a two mirror laser cavity with a plane M prime coinciding with a cavity mirror. So the cavity mirror then should be placed or should be coincident with the line M prime. The negative group delay dispersion will be half of the full combination. The four prism combination also produces third order dispersion phi triple prime, which depends on the separation between the prisms, the prism material, and the operating wavelength. Chirped multi-layer dielectric mirrors can be used instead of ordinary mirrors to compensate dispersion. Such mirrors consist of many low and high refractive index layers arranged alternatively, with the thickness of these layers to increase progressively towards the substrate in a well-designed way. So you see that we can also use the chirped multi-layer dielectric mirrors to compensate the dispersion also. High frequency part of the beam is reflected first. Now you see that as far concerned with chirped multi-layer dielectric mirror, now I am going to give you the what happens physically when we use such mirrors. High frequency part of the beam is reflected first, and the low frequency part is reflected from depth. Thus, the reflected beam has a group delay dispersion which increases for decreasing value of omega, thus providing a negative group delay dispersion. Phi triple prime can be made, phi double prime can be made negative. The multi-layers can be designed to produce group delay dispersion independent of the frequency. That is, we can set phi triple prime approximately equal to 0. The magnitude of phi double prime is small, and thus multiple reflections between the chirped mirrors are required to produce a significant amount of negative dispersion. So you see that we have discussed two negative dispersion techniques with that we can introduce. One was based on the combination of the four prisms over here. So this is one way of producing a negative but controllable second order group delay dispersion. And the second technique is what I have mentioned, that we can use chirped multi-layer dielectric mirrors can be used to control to have a control over to introduce negative dispersion. So this is the end of a presentation. So this is the end of slide number 135.